In this video, we'll look at a few examples of how the linear model can be used to solve application problems in statistics. Here's our first example. Suppose that the correlation between the number of hours a child spends watching television in a month and monthly household expenditure in dollars on toys is R equals 0.52. What fraction of the variability in dollars spent monthly on toys can be accounted for by hours spent watching television? This problem is pretty straightforward and requires us only to calculate the R squared value. R squared is equal to the correlation raised to the second power. So R squared is equal to 0.52 squared, which is approximately equal to 0.2704. We can then say that about 27% of the variability in monthly toy expenditures can be accounted for by hours spent watching television. Here's another example. A cell phone carrier was interested in determining whether the number of texts customers send each month, our X variable, influences the amount of time spent in conversation on the phone, our Y variable. A random sample of 25 customers were selected and their data usage was reviewed. The following summary statistics were generated. The mean for X was 51.64. Standard deviation for X was 27.03. The mean for Y was 159.4. And the standard deviation for Y was 40.35. Our correlation was negative 0.981. The first thing we want to ask ourselves is whether or not a regression model would be appropriate for creating a linear model of this data. And the answer is yes. The reason why is that monthly number of texts and monthly phone minutes are both quantitative variables. Our correlation R of negative 0.981 implies that our scatter plot would be linear, going in a negative direction with a fairly strong association. So yes, a linear model would be appropriate in this case. Since we know that the model is appropriate, what is the regression model for predicting monthly phone minutes based on monthly text usage? To construct our linear model, first we need to find the slope. We use the formula b sub 1 equals r times the standard deviation for y divided by the standard deviation for x. By plugging in our values, we get the following. Negative 0.981 times 40.35 divided by 27.03. When we calculate this, our result is negative 1.46. That's our slope. Next, we need to calculate our Y-intercept. Our Y-intercept is given by the formula b sub 0 equals the mean for y minus the slope times the mean for x. Using our data, we'll plug in our values to get 159.4 minus our slope, which is negative 1.46, times our mean for x, which is 51.64. b sub 0 is equal to 234.79. Now we'll use information from our slope and y-intercept to build our regression model. Our regression model is y hat equals 234.79 minus 1.46x. Using the model, what would you predict the number of monthly phone minutes to be for 500 texts sent in a month? To calculate this, we'll replace x with the number 500. our result turns out to be negative 495.21. Think about that answer. What's wrong with the result, negative 495.21? The problem with our result is that we've predicted a value for y that's a negative number. Within the context of our data, you can't actually speak a negative number of minutes on the phone over the course of a month. This result would indicate that using the number 500 within this model would be extrapolation. In other words, our linear model may be effective, but it's most likely only effective for values far lower than 500. The way to determine this for sure would be to look at the maximum value on your x-axis. In this case, we didn't have the individual data points to evaluate. However, by getting this result, we can assume that our model is not designed to accommodate values as large as 500.